So this is a neat little review paper, but almost 10 years old. It doesn't matter, the messages are still good. And the paper has lots of discussions on some of the industries that need to reduce emissions, like steel and cement, for example, and what the outlooks are for each of these energy systems and approaches to reducing the emissions from industries that are high on the emissions list and so on. I'm not going to go into those kinds of details, but just make a few brief points, and you should definitely look up the paper if you're interested in an overall review. Okay, so start with this schematic of an integrated system that can provide essential energy services without adding any CO2 to the atmosphere. And then there are some color codes here. So green is, of course, the electricity generation, and everything includes transmission or transport as well. Hydrogen production and transport are in blue, and purple corresponds to hydrocarbon production and transport, with orange referring to ammonia production and transport. And you have red for carbon management and black end uses of energy and materials. So lots of color codes, but the schematic is basically on the top with demand for highly reliable electricity, and we have looked at the kind of nanogrid, microgrid issues in bending the curve, where you have similar figures where everybody is feeding into the grids, and then people are also plugging into the grid or giving it back to the grid, depending on whether they are idling or they are charging for transportation. For B, you have demand for structural materials which require energy, so cement and steel with capture, for example, coming in here in terms of end use of energy and materials. And cement and steel have emissions from the production processes themselves, like melting the iron ore to extract the small amounts of actual iron that's in them, versus cement, which is splitting calcium carbonate into calcium oxide and producing lots of CO2. And they have energy requirements on the other end as well, so you have to be careful which part you are discussing here. They are mostly talking about the emissions from the industries themselves. Demand for aviation, long distance transport and shipping, which are big contributors to the energy demand, hence they have to be taken into account for net zero energy systems. So then go to D, which is ammonia plant. And there are various issues about how to make it usable energy and how it gets used and transported, etc. You can of course also feed it with hydrogen to produce ammonium. So we'll see the table on what processes can be used. You have also hydrocarbon productions like CXHYOZ, OZ, which are generally producing things like syngas, so it can be carbon monoxide and water, or it can be H2O and CO2 producing oxygen, and you feed that also into the energy demand for transportation, or you bring it into producing synthetic gas liquids, which are some things that are converted to hydrocarbons. So that's the CXHYOZ as a general formulation, and it feeds into the natural biomass syngas with capture. Every time we say with capture, that's carbon capture and sequestration. And capturing at source is of course now quite feasible, and economic issues have to be considered, but in general the idea is we cannot live without carbon capture at this point anyways. Okay, the difficulty of course is doing what is called DAC, direct air capture, because the carbon dioxide concentration is too tiny, 0.04%, and the energetics of doing that efficiently don't scale up so far very large to very large systems. There are many implemented systems which remove something like a few hundred cars off the road per year based on their capacity, for example. Okay, so you also have various ways of producing hydrogen. So let's go from D to, I jumped around a little bit, but E is here. So everything we capture, we need geologic storage, and F is here with synthetic gas and liquids, which is receiving input and giving out output to the hydrocarbon production here. And G is of course cement and steel that we mentioned, and it can be done with capture to reduce emissions, in addition to other things like electric arc furnace that would be needed for reducing energy use in smelting the ore, or renewable energy for doing there are green cements which change the process itself, but then if you use the process of producing clinker, then you need to worry about capture as well. So there is the output coming in here. So you have CO2 coming in. So if you go from G to H, we already looked at direct solar fuels here, and you have I, which is biomass, gas and liquids. So you have the biomass being produced, fed into the system, which can go into producing syngas or into hydrocarbons, and of course they can feed of course here into natural gas, biomass, syngas and capture as well. Okay, so that's I. J is direct air capture, and HIJK, hydropower pumped storage. So the green ones are electricity generation and transmission. So you need hydropower, nuclear for green energy sources, along with wind and solar. We touched on all those, so you can see the solar fuels being used to produce hydrocarbons as well. So it's always a battle between going to net zero by decarbonizing versus dealing with irreducible carbon and having carbon capture to take them out. So emissions will not be zero or negative. You will have emissions, and then you will draw it down or draw down more than you are emitting to reduce CO2. And then you have electrolysis to produce H2O, which we'll look at in a bit more detail. L, M, N, O, P. M is natural gas, biomass, syngas, which we already mentioned. N is here nuclear. O is solar. Sorry, I jumped around a little bit. P is hydrogen and synthetic gas. So you have the blue line for that. We'll look at the table to look at some costs and so on. And you have other centralized storage, so thermal and batteries. So deal with a mix of dispatchable powers like hydro and nuclear or biomass, where you can send electricity or crank up the production when the demand goes up, versus the non-dispatchable ones like solar and wind, which have intermittency and cannot be cranked up whenever you want, depends on when they're available. Then you need centralized storage, thermal and batteries, so you can do warming certain liquid and storing the energy and re-releasing it and so on. And you have things like compressed energy storage, where you use energy to store compressed air and then drive turbines when you want energy by using that. And S of course is wind. Okay, makes sense, right? If you look at key energy carriers and the processes for interconversion, their processes are listed in each cell. Convert the row energy carrier to the column energy carrier. So they provide details and efficiencies elsewhere. So you're basically trying to produce electrons which flow and give you electricity, which is energy. Then you have H2, which can be produced with electrolysis at the cost of $5 to $6 per kilogram of H2, pegged to some year as a reference. Then you can have electrolysis plus Fischer-Tropsch, which is the way to convert syngas, CO plus H2O mix, into hydrocarbons, the CXHYOZ that we looked at, which is here. So that's also can be done with electrolysis plus methanation, where you're producing methane. So methanation is done now at $0.07 to $0.57 per meter cube of methane. So we are looking here now into H2 production here as well. So on the row again, ammonium production, again electrolysis plus Haber-Bosch. Haber-Bosch is the Nobel Prize winning process that facilitated fertilizer production at large scales industrial scale ammonium production, which of course also led to nitrogen bombs. Many people complain about that. Nonetheless, this brought about green revolution and food security for large populations like China and India. So down the column you have H2CXYOZ, HZ, and so you remember this is what we looked at before, and ammonium. So you are kind of cross-correlating things. So hydrogen can be produced with combustion or oxidation via fuel cells, where you're directly extracting electricity. Hasn't gone far in terms of fuel cell cars, for example. Some people say it's already dead, but nonetheless, which one is more energy efficient becomes very important. But you can also go from H2 to methanation, as we said, and the Fischer-Tropsch process at $4.40 to $15 per gallon of gasoline equivalent hydrocarbon. Okay, and H2 can also be used for Haber-Bosch to produce ammonium at $0.5 to $0.6 per kilogram of ammonium. Generalized hydrocarbons can be produced by combustion or biomass gasification, which costs $4.80 to $5.40 per kilogram of H2. This can also go to producing H2, row carrier to the column carrier. So H2 can go to produce hydrocarbon by steam reforming and feeding the hydrogen, as we saw before, from $1.29 to $1.50 per kilogram of hydrogen. And of course you have again steam reforming and Haber-Bosch to produce hydrocarbons. Ammonium again, you can produce the electron with combustion or sodium amide, or what's called sodamide. It's like a rock salt kind of thing, which is highly combustible with water, and can produce H2 for ammonium with metal catalysts at $3 per kilogram of H2. You can produce ammonium from hydrocarbons with metal catalysts, methanation, or Fischer-Tropsch processes. So it's kind of a matrix which gives you a sense of what are the combinations of things and what are the costs involved. One of the points made here is of course that there are difficult to eliminate emissions in the current context, which will make carbon capture and sequestration, or carbon capture, utilization and sequestration, an essential component of net zero. This is of course debated because this is a technological promise on which we are relying for future projections of net zero, which have no guarantee of coming true in terms of the promises being fulfilled in terms of scalable direct air capture, for example, or pushing CO2 into the ocean, and so on and so forth. So here we are looking at global fossil fuel and industry emissions for 2014 at 33.9 gigaton CO2, not CO2 equivalent. So the numbers with non-CO2 gases will be higher. And here you look at difficult to eliminate emissions in 2014, which were at 9.2 gigaton CO2, which is a significant fraction of almost 1/3 of the total emissions. So you have to pay attention to the various pie chart components. Other industry, residential and commercial, these that jump out are the irreducible emissions. So you have aviation and shipping, so long distance road transport with 1% is a part of it as well. Short distance light road transportation can be reduced in various ways. Short distance, medium and heavy road transportation can be reduced. Long load following electricity, often these so-called peaker plants are driven with coal to supply the additional energy demand when it comes in, let's say during a hot day or a cold day for cooling or heating. Electricity production, so the steel and cement are split here partly into irreducible emissions, as well as they are also here in terms of energy use versus direct emissions from the industry and so on. So you have to be careful of that. So heat, combined heat and electricity, and so on. And if you look at what adds up to the difficult to eliminate emissions, load following electricity is a lot of it. 4 gigaton CO2 in 2014. Iron and steel added 1.7. They have different cement is not included in here with the iron and steel. It's separated into 1.3. So shipping, rail ships and others, aviation and long distance transport. So these are the kind of things that these are the emissions that may be irreducible even over to 2050 and beyond, in which case CCS becomes incredibly important. But also all kinds of assumptions go into estimating these. For example, here that'll come in the next chart. For example, if you look at comparison of energy sources and technologies, you are looking here at the estimate of the relationship of capital cost or electrolyzer cost and electricity price on the cost of produced hydrogen, which we will look at here, the simplest possible electricity to fuel conversion right now. This assumes a 25-year lifetime, 80% capacity factor, 65% operating efficiency, 2-year construction time, and straight line depreciation over 10 years with zero salvage value. So I just wanted to read it off because enormous number of assumptions go into estimating costs, especially into the future, because things like discount rate or this straight line depreciation over 10 years are very controversial. Depending on which rate you use, you can get very different numbers. Basically, you can think of it as how willing are we to invest now for the future, knowing that it's the future generations that will be benefiting from it. Will the dollar we put in now depreciate at 3%, 5%, 7%, or 10%? That determines how valuable the investment is in the current dollar. So this gets quite hairy. Just looking at comparison of energy sources and technologies, gravimetric density in millions of joules per kilogram. I hope I'm right on the unit, so you just make sure. Yeah, please check it out. Okay, and volumetric density as well. Could be megajoules, millions of joules, the same thing. So gravimetric density versus volumetric density per kilogram per liter. So lithium ion battery sits here at the corner with zero gravimetric or very small gravimetric density and very small volumetric density. You jump to this end with very low volumetric density with hydrogen at 350 bar, at 7 bar, and in liquid form. So obviously energy density of hydrogen is very low at low pressures, and to transport it also it becomes easier, and the energy density in terms of volumetric density will grow even if gravimetric density is same. So this can tell you a lot about why hydrogen is still not a big part of the game compared to, let's say, lithium ion and other things. Methane sits here in terms of volumetric and gravimetric. Ammonia is here, methanol, ethanol, propane, and methane. You have various levels of gasoline, jet fuel, and diesel. What do you do with it? Basically, you have to see how they convert also in terms of production per unit of electricity, let's say. So this is done here in terms of variable cost in dollars per gigajoules and fixed cost of energy in dollars per gigajoules, or fixed cost of energy in dollars per kilowatt hours. Kilowatt hours can help you think more about how much a typical household uses in a month and so on. So you have basically variable cost being almost zero for geothermal, onshore wind, solar PV, offshore wind, and solar thermal. But variable cost is zero, but fixed cost can vary depending on the implementation. Okay, so hydro comes in here with small variable cost and fairly high fixed cost. then coal with carbon capture, biopower, natural gas without carbon capture and sequestration, natural gas with combined cycle or driving a turbine. Combined cycle is where you are doing electricity and combined heat and power, for example, and so on. And these are the isoplets of costs in dollar per gigajoule. Okay, so these have to be taken into account. And of course, producing electricity from hydrogen fuel cell kind of thing, dollar per kilowatt hour versus capital cost in dollar per watts. You can see that methane derived H2O sits here at this point, and as you increase the electricity cost, then the capital cost both have to be balanced. If you can look at grid scale storage in terms of cycles per year and levelized cost of discharging electricity at dollar per gigajoules, this assumes, for example, comparison of the levelized cost of discharged electricity as a function of cycles per year, assuming constant power capacity, which is an important assumption, 20-year service life, and full discharge over 8 hours for daily cycling or 121 days for yearly cycling. Dashed lines here for lithium, lithium and hydrogen are aspirational targets, which means you would want to bring the levelized cost of discharge electricity down to this level, and for lithium down to this level, depending on the number of cycles per year. So obviously, as you increase the number of cycles, whether it's pumped hydro, compressed air, H2O, lithium, or flow batteries, become more cost effective in terms of levelized cost of discharge electricity in dollars per gigajoules. But you can see that hydrogen flats out after about 20 cycles, so you want to bring it down here even if it flats out, and lithium target has to come down here to meet the levels of hydrogen or better as well in terms of cycles per year against cost of discharged electricity. So as I said, there are tremendous amounts of details in the paper that you should read. I just kind of gave you a very brief account of it. So I think I'll leave it here. This goes well with the other things we are looking at in terms of reducing emissions in steel, cement, food systems, and so on and so forth. Okay.